is. Okay, right. Okay, right. Yes, there is a screen now, and so I was going to start with motivation and how I got into this thing. And so originally I've been looking at blocks of group algebras of tame representation type, and there are not, so what do I do here, this one here? So there are not so many, and they occur only for certain grouped, I mean, these defect groups is a group theoretic invariant. It's not really very important for algebras, but it's just the background. Anyway, so this is been known for some time, and one would like to understand the classification up to Morita equivalence. So in the long time ago, I introduced algebras, which I called dihedral, semi-dihedral, quaternion type, and they are defined by given by equivalent relation, and blocks appear as special cases. And so in some sense, this put the blocks into a wider context. And so I've given one example here. So quaternion type, that's perhaps the most interesting one. So this is Tame Symmetric, and it must have a non-singular Cartan matrix. So this is the matrix which has Cij is dimension of EI algebra Ej, and all simple modules should be periodic of period 4. And so this condition on the Cartan matrix comes from group theory, and it is very strong because you can deduce from that simple modules, there are only few simple modules, and which is, of course, it was known for group representations. However, in some sense, it makes life easy. And so anyway, so at that stage, there was a classification. And then I worked with, I should have said that much of the work was joined with Andrew Skowronski. And so we discussed many properties of these, Skowronski. And decided at some stage there couldn't be more algebras, which was, however, wrong. So about 30 years later, cluster theory developed. And so in cluster theory, there are algebras constructed from surface triangulations. And so Sefi Latkani told us about some examples which looked like the quaternion type. So tame, symmetric, all simple modules are periodic of period 4, but the Cartan matrix condition didn't hold, right? So this was a bit of a surprise. And so, yeah, of course, then we would have to follow this up, because we made a mistake and we had some examples, the ones from blocks, and so we should continue with that. And so that's where this started off with. So this was about 2000. So how do I do that? Right. Okay. So then we worked on, of course, on algebras. And so yes, so I'm going to describe the algebras now we study, and then come to the hybrid algebras, which I had promised. Anyway, let me just first ask, of course, I wasted 15 minutes because, yeah, so do I still get 15 minutes or so, which means till roughly, yeah, so this would be maybe past whatever the hour is in Iran. So it wouldn't be past, but so I wasted
4:15, up to 4:15 in Iran times.
In Iran times. So 4:15 Iran times is 2:45 in British time.
Yes, yes.
Okay. All right, okay. Right, so now I wanted to talk about algebras. So since we are interested in Morita type, then we can work with finite dimensional basic algebras. And so I'm taking field algebraically closed field. And so I'm only talking about tame and symmetric algebras and consider finite dimensional modules. So the property tame is quite strong. And as we have seen for blocks, most blocks are not tame, but anyway, it's still an important thing. And symmetric, so blocks are symmetric. And so for symmetric, the things I'm using is so projectives are injective, so projective is the same as injective. And I'm also going to use that the Ausländerreiten translate is the same as omega squared. So this is very important. So, right. So, okay, so what quivers can you have? For tame, you cannot have too many arrows in the quiver. So, tame. Not too many arrows, few arrows near a vertex, For example, you cannot have something like that. You cannot have triple arrows. This is not forbidden, not allowed, and other things. So anyway, so in nature, most of the algebras which we know, the quiver is too regular. So which means that for every vertex, 2 arrows start and 2 arrows end. So locally like that. Right. So now there is the idea of a biserial quiver. So you're not just having a quiver, but you also have a permutation of arrows, which so that you can compose alpha and F alpha can be composed, right? And yes, right. And so sometimes it happens that, okay, so I should do an example here. I have a small example. Omega 2, 3. And here I have another. So it should be a 2 regular quiver here. Epsilon rho. And here is alpha 1, alpha 2, alpha 3. So we could have F to be written it as a permutation of arrows is alpha 1, alpha 2, alpha 3. And take all the loops extra. Right, and so then this would be an example. And then in this case, you see that F cubed really is the identity. And so this would be an example for a triangulation quiver. However, if you take a different F, you could take F to be different. So you just take it as omega alpha 1, epsilon alpha 2, rho alpha 3. So this has then F to the 3 is obviously not the identity. So this is not a triangulating quiver, but it still is a biserial quiver. Right, okay. Okay, so this is the ingredient. And so, okay, so if you have this quiver, you can always, you always have 2 arrows from each vertex. And so here is alpha 1, and then you also have alpha 1 bar, which would be the other arrow which starts at the same vertex here, right? So you have always alpha and alpha bar. And then you can, since if you have F, then you can also take the other permutation. So you take always the other arrows starting at the same vertex. So what? So if you have F alpha is 1 arrow, then you have G alpha is always the other one, right? And so, yes, right. So this was omega before, I think. And this was, don't know what it was before, epsilon and rho, epsilon and rho. And so, yes, right. So in this example here, do this differently. So we had, if we have F to be alpha 1, alpha 2, alpha 3, and the 3 loops. So then G is always the other one. So you have alpha 1, you can't go to alpha 2, you take epsilon. So from epsilon, you have to go to alpha 2, and then you go to rho, and then you go to alpha 3, and go to omega. So anyway, so you always have 2 permutations. And yes, right. So later, the idea is F should encode relations and G describe the basis. So I should just mention that these occur for Bauer graph algebras. So there is, if you have seen a Bauer graph algebra, then there's always a graph to that, the Bauer graph, and at each vertex of the graph, you have a cyclic permutation, and this corresponds to the G. And there's also something which is called sometimes a green walk, which comes from group theory again, and this would correspond to the F. So they are somewhere already there, but you can do this more generally, right? Right, so in joint work with Anju, we introduced various types of algebras, which generalizes quaternion type and dihedral type, etc. further. And so we defined them by equivalent relations, And I don't want to go into the details here because there are too much of them. And I have already been wasting time anyway, so I won't do any more details. But anyway, so finally we got to introducing what we call hybrid algebras. And the reason for calling them hybrid algebras, it was actually before the lockdown, i.e. before hybrid meetings happened, but it was meant because they at the same time contain the periodic algebras, the quaternion type, and also all the other ones. And so in some sense, they would be hybrid. Right, so let me introduce that. So we have this, we have already introduced biserial quiver here. And yes, right. I think, look at an example again, alpha 3. Right, so then we have a permutation G, which is a permutation of the arrows. And so we can look at the path. So let me just take G to be the one which we had with the 2. So epsilon 3. And so we can take paths in this quiver following G here, but it should be a cyclic path. It has a length, so maybe, okay, so this has a cycle of length 6. So the n alpha is the length of the cycle, And m alpha is some multiplicities. So we take a cyclic path which walks around this G cycles. And so when it comes back to its origin, it has a multiplicity. There's a multiplicity, and the multiplicity must be constant on cycles. So we take this element in the path algebra. This is NKQ. And then we take another path which has not quite the same length, but one less. And so with this data, we can define an algebra. So we take a set of arrows in this quiver, which must be fixed under invariant under F, and F on this set should be the identity. So in this case, we can take T to be just alpha 1, alpha 2, alpha 3. This would be okay. This is not everything. It's just one cycle of F, because F here was alpha 1, alpha 2, alpha 3, and lots of loops, right? Omega, epsilon. So this would work. And so then we define our relations. So inside, within this outside T, then the relation should be 0. And inside T, then we take a different relation. So the relation in this example would be omega squared should be 0. So omega squared is 0. And epsilon squared is 0. And rho squared is 0. But alpha 1, alpha 2 should be, yeah, I mean, this should be a multiple, scalar multiple, whatever it is, by this monomial A alpha 1 bar. So this would be alpha 1 bar. And so this would be A omega in this case, right? And so similarly, you can write down completely the all relations. Then you have some 0 relations here. Oh, sorry, this should be 0. And there are some exceptions because, yeah, for technical reason, I don't want to go into that. And so this here is basically a Sokal relation. So this is tells you that B alpha spans the Sokal of the and so this makes sure that the algebra turns out to be symmetric. Right, so there are special cases. You could have that T is empty, then you get a Bauer graph algebra. Or special biserial if you want. Maybe special biserial is better. Sometimes called special biserial. And these were the algebras which appear in the dihedral setting. But if T is everything, then you get a periodic algebra. So these have period 4. But you can have anything in between. For example, you can take, you can show that all local Tame symmetric algebras occur, and all blocks of Tame, almost all blocks of Tame type, and actually all blocks of finite type. So Bauer tree algebras would all appear as well. Right, so yeah, so seeing that, of course, you might ask how many Tame symmetric algebras occur in generally. I mean, there are a few more, so here is an almost, but all the examples we know with the almost would actually be derived equivalent to the ones here. So I mean, think it's quite likely that this is a very large class, and quite possibly you have, yeah, close to have a full list of Tame symmetric algebras. Anyway, that's what I think is the case. And right. So how far did I get? Right. Okay, so if you want to show that, so problem is show that can we possibly classify Tame symmetric algebras in general? And so, I mean, this is too open-ended, but we can assume that the Gabriel quiver of that, the Gabriel quiver is is too regular. Right. So yeah, I mean, this is a nice condition because you have more symmetry than in general, and you avoid some technicalities. Anyway, so if you wanted to classify algebras, so historically, but for finite type, perhaps describing the Riemann strategy. So Riemann basically, and so symmetric of finite type maybe, finite type, showed that the stable Ausländerreitenquiver is, yeah, what is it for finite type? Z delta modulo some group, and delta is Dünkin, right? ADE. And so then she and various collaborators considered all algebras with such a Ausländerreitenquiver and well, okay, it's stable and you don't have any projectives there, and you put back the projectives, and so then you classify the algebras, right? And so for the original blocks setting, blocks of Tame type, I basically did the same, except of course the stable Ausländerreitenquiver is not that. So gamma S is something different, is known basically. And then I also took this stable quiver and put all the projectives back and classify the algebra. And so basically we're trying to do the same here. I think this ought to be a reasonable strategy because, yeah, I mean, what else can you do? Right. And so as a first step, try the same strategy. So the first thing is you need first task is what is how does the stable Ausländerreitenquiver looks like, right? Yes, right. Yeah, so question actually, I mean, I'm not really quite sure. I mean, I have looked at some websites and seen that you have some work on finite dimensional algebras where you have stable Ausländerreitenquivers, or should I say something about what this is? And
if you remind the definition, I think.
Just reminding the definition, yeah, right. So yeah, okay, what can I do? I can add a page here, right? Okay, I know how to do that. Oh, this was not the right one. Ah, yes, okay. Right. So I hope I can get back to it. Yeah, okay. Right. Okay, right. So okay, so Ausländerreitenquiver. Okay, so I needed to write again. Okay, so the Ausländerreitenquiver encodes the almost split sequences. Yeah, almost split sequences. So you have some okay, so here we have tau m, and there's some E and M. And so you write this as a direct sum of indecomposables, and so you write it as a graph here. So there's tau m, and then you have E1, E2, and so on. And yes, so the stable for the symmetric case, so our algebra is symmetric. So just remove only the projectives. And so this would be finitely many. And this uses that the algebra is symmetric, right? Because the algebra is symmetric. So you don't have orbits which get cut off. And so you would just produce a few holes, right? And so, yes, right. And so remove projectives, and so you get, so this is a translation quiver, right? So gamma S is a translation quiver, has a translation. And in our case, because it's symmetric, it's the same as omega squared, which is the syzygies of this modules, right? So here would be a tau of E1, because we have this translation, and here we have tau of E2, and so on. Oh, sorry, this is the wrong way around. Right, and so there is a lot of symmetry, and so Karin Erdmann has the classification theorem, classifies translation quiver. And so in general, and so in the case we're looking for is we can show that, so the main result is showing that if we take a component, then it is isomorphic to ZT, and T is either Euclidean or A infinity, A double infinity, or D infinity, or could also be a tube. So I should get back to my picture. And so, for example, D infinity is perhaps interesting because it isn't quite looking like regular like that. So it's something like that. So it goes infinite in all directions, and yes, right. So okay, so why is it type D? I suppose you can see that there is a type D diagram sitting in here. Well, you could take some cross sections here, one from each orbit, so you get here type D. This is D infinity, and here you have a way in taking Z many copies and glue them together, right? So this is about, right? Okay. Okay, so this is what occurs in the setting of Tame symmetric algebras, and in examples for weighted surface algebras, these were the quaternion type. They are periodic. So it's periodic, and you get only tubes with R at most 2, and so this would mean that omega to the 4 is the identity, because tau is omega squared. And for the dihedral type, then this is really the same as special biserial. And this is known for some time that that the components are A double infinity apart from tubes, right? Okay. And so for semi-dihedral type, I haven't talked about that very much. For the group setting, you get also A infinity and infinity and D infinity. And so in some sense, all these things do occur here. And yes, one question I don't know is, for tame algebras, so lambda tame, can A infinity occur? Sorry. Tame and symmetric, right? And so no examples are known, no examples. You have tubes, but no, not just ZA infinity. And I think this is one of the challenges which I think need to be understood, why this cannot, maybe it can occur and we just haven't found examples, but yeah. And of course, the other question is, remove the condition that Q is too regular. I think this is only because of the proof and it's not really a condition, right? Okay, right. So I think for the rest of the time, I was going to talk a little bit about how you can prove that. And this is some homological algebra. And yeah, I mean, for Auslander-Reitenquivers, for hereditary algebras and many algebras, finite global dimension or triangular quiver have been studied a lot, but somehow the self-injective or symmetric or it's different. I mean, yeah, they're just different. And so I think there are not so many tools for. Yes, so how about the proof? So basically discussing something about the proof. So what sort of tools do you have to identify? So we have a component of the stable Auslander-Reitenquiver, and we'd like to know, we know it's isomorphic to ZT or perhaps ZT modulo some group. And so the question is, what is T, right? Right. Okay. So there is some old paper by Happel, Preisel, and Ringel. Happel, Preisel, Ringel. Where they introduce, well, this is based on paper by Winberg, they introduce additive functions on the component. And so using additive function, you can identify, if you have suitable additive function, you can identify this T here. So yeah, so in this context, what we can do to find such functions is we use homological algebra. So we take an indecomposable module in our component. Of course, it will not be projective or injective. And so if we take any module, we can define a stable dimension. So this is a typo. This should be lambda. And this is from lambda. Modulo maps which factor through projectives. So we have the space W M projective. So this is in the stable category. So the tool is, if you have a periodic module, so it should be omega squared W equals W, and this function is non-zero, then the tree class is if this component is as in the theorem, right? So yeah, so the thing is that with this function here, you can use homological algebra and you can see what the symmetry on this component is, right? Right, so yeah, so where does this come from? I mean, it was first used by Peter Webb and Okuyama in the group setting. And however, for group settings, you have more technology. And so we have modified that for self-injective algebras and came to this formulation. So what you have to do is, the first thing is you have to find a suitable W. And so then the second step, which works in this case here, if you have a W, So, okay, so having with such W, we have to analyze stable homomorphisms of W with this module, of course. And so what works in this case here, we can show that if this is 0, then module M is actually periodic. And this actually does the trick, because in this case, then theta is a tube, because periodic modules are in a tube, and we know what theta is. And otherwise, we have a non-zero dw non-zero. And then we can use the lemma, so we are done by the lemma. So that's enough to do, right? Right, so 2 things to do. One is finding W, finding suitable module, and the other one is actually doing the hard work and showing that the stable homomorphisms are 0 in this case, right? Okay, if they are 0. Okay, so I think the construction of W is interesting, because this is the place where the 2 regular quiver is used. And so I should turn my page now. So why does it not work? Right. Okay, right. So if the quiver is 2 regular, then we have a separated quiver, and it's always a disjoint union of bipartite quivers, isomorphic to A tilde for some n. And I think I have an example here which I'd like to draw. So my quiver is now so it should be 2 regular, but I don't want loops here. What I'd like is I have a pair of arrows here. Yeah. So this is beta, and this is gamma, right? This is 2, and this is 3. And I was going to draw the separated quiver of that. So how do you do the separated quiver? You take each vertex, and you take another copy of that, and you draw arrows here. So if I take this one here, 2 here, then I have arrows from 2 to 3, but I call this one 3 dashed because it's a separated quiver. So I have 2 arrows going here. There's alpha 2 and gamma here. No, this is beta, right? So this would be one of the components of the separated quiver. I've got another one. 1 goes to 2 to 1 as well, dashed. So this is omega. Then there's also 1 to 2. And yes, what else is there? Should be a 3. So I have a 3 from 3 to 1. So that's this arrow here, alpha 3. And then I have an arrow from 3 to 2 as well, which, yeah, it should be going somehow underneath this thing here. So this is the arrow from 3 to 2, which is called gamma. Right, so this is a separated quiver. And so, yes, right, so if I take one of these components here, so I take this component here, this is the most interesting one perhaps, then it has a 1-parameter family of modules of period 1. So in this example here, we can draw it very easily because this is just a Kronecker quiver. So we have a two-dimensional vector space, V and W. And so here we have one action beta. It takes V to W. And then we have alpha 2, which takes V goes to lambda W. Sorry, this is badly written. So this is basically a multiplication by lambda, right? And lambda should be in non-zero. And so this is a one-parameter family of modules. They have dimension 2 in this case. Dim W is 2. And actually, each of these things will produce a tube in the Auslander Eigenquiver. But anyway, they have tau period 1 as modules for this quiver here. But the important thing is that we can view them as lambda modules. Right, so basically what we do, we have lambda modulo radical squared, and this is identified with the separated quiver in the suitable way. And so we just inflate the representations. So, okay, so question is, what are the properties as lambda modules? Yes, right. So there is this old paper by Bill Crowley-Bowie, who has studied tame algebras, and he proved that if I have a tame algebra, then almost all modules of a fixed dimension, so almost all indecomposables. For each dimension D, almost all indecomposables of dimension D have tau period 1. Right, and so in this case we have modules of a fixed dimension. In this case it was 2, otherwise they're also fixed. And so they must have tau period 1, and so in our case it's omega period 2, right? Okay, right, so yes, so this is black magic. So we take the theorem, and so we would know if we inflate them as lambda modules, they are also periodic. And so we can take these things, one for each component. So take one of these things for each component and take the direct sum. So direct sum over all components. Components S. And then, of course, we have scalars, so we have some freedom. But even if there are some which are not periodic, we have enough elements in our field, and so we can find some lambda so that they're all periodic. And then we have a module W, and this one actually works, right? Good, right. So we have a module W. So what do we do then? Yes, I don't know how much detail I want to say. So now we take this indecomposable and non, so we know we are at the step 2 here. So we take this W and we take indecomposable, not projective. And yes, so we want to show that if stable homomorphisms from W to M is 0, then our module M is actually periodic. That's what we wanted. And yes, right. So yeah, I mean, here gets technical, and I can say one word for this one here. So e.g. in A. So this module W0, it has radical length 2. as in our example here. So we just have a top and a socle. And so, yes, so, and you show that if a map and the image is not in the socle, then you'd have to show that the class in F, class of F is, so sorry, don't want to have, then F factors were projected. So that's what you have to do, and this is actually not so difficult. And so this gives one inclusion, and the other one is similar, and part B is dual to that. Right, so if you put these things together, you can show that whenever the stable homomorphisms are 0, then the top of M is isomorphic to the socle of M. And I'm not going to discuss that, but I'm going to explain the consequence, because this uses a Crowley-Bowie again. Okay. Right, so maybe I can take a new page for that. Okay, so we have, so what do we want? A proof of the corollary. So we have, if from Wm is 0, then top M is isomorphic to soc M, right? Okay, and so we want to show that, so the claim is that M is omega periodic. And this is actually rather nice, and it is really only a consequence of Bill's theorem, because how do you do that? So we have, from construction, we have omega W was isomorphic to W from construction. So we're looking at the stable homomorphisms from W to omega n M. Yes, so stable homomorphisms are invariant under omega. So this is isomorphic to hom. W is omega NW. And this is isomorphic to hom W M, which is a property of stable homomorphisms. Omega is an equivalence of the stable category. Right. So, and this is true for all n in Z. So we can apply, then we can use this one also for, so star also holds for omega n M for all n. And this is enough information because we have soc omega n M is top omega n M. This was star here. And so now we use that the algebra is symmetric. This is the socle of omega n plus 1 of M, because if we take a projective cover of omega n, then yes, the kernel of that is omega n plus 1m, and in the middle we have a projective injective which has top equal to SOHCAHTOA, and so you can keep on doing that. And so we have that top omega n m is the same as top omega m for all n. And so this tells me that the dimension of the modules omega n m must be bounded, because the projectives appearing are always the same, right? So this is very good, because then you have again a dimension d, so that infinitely many omega n m have dimension d. And so by Cowley-Bowie again, the same theorem with Tame algebras. One of these is periodic, at least is periodic. Omega periodic, but of course, yeah, I mean, we have a set of syzygies of M. If one of them is periodic, then M is periodic, right? And so M is periodic. So I think this is quite nice, because it doesn't need any presentation. And in fact, I've proved this one, this component theorem first for hybrid algebras with a lot of technicalities, but after I've done it, then I noticed that I don't actually need it, because it is just Cowley-Bowie's theorem. Yeah, right. Anyway, so I think this is probably about what I wanted to say. And we worked out with Andrew what the components containing simple modules look like, and you can describe them. And you can see that always d infinity occurs when you have a simple module where one of the arrows starting at the vertex is in T and the other one is not in T, then you get these things. But anyway, you can do that. But I think my time is pretty much over. So yes, right. So I think I'll stop, and thank you very much for your patience, and I apologize for the mess with the iPad. Thank you. Right.
Thank you very much for your very nice talk. Are there any questions, comments?
So anyway, if you have some ideas about Ausländer-Reiten components of symmetric algebras, let me know. So I don't know whether you're looking at Ausländer-Reiten components at all. Maybe other types of algebras, yeah. I mean, I have looked at some papers, but I mean, finite type is you have some papers on finite type, yeah? Somebody has, I don't know.
And I have a question. In general, is there some criteria for asking about the type of the symmetric algebra or not? I mean, for example, for hereditary algebra, we know that by using the quadratic form, we can characterize, for example, finite types or tame types. But for symmetric algebra, if we have such criteria or...
Yeah, I mean, nothing I know. I mean, if you have I suppose it's a symmetric algebra, then okay, so you have a quiver. I mean, first of all, the separated quiver has to be tame type. I mean, otherwise you would have. I mean, okay. So one thing you would know is, don't know what. Anyway, sorry. Yeah, okay, so if the algebra is symmetric, sorry, does it? So what do we know that, of course, for Tame type, you're asking for Tame or in general or what? General type.
For
Okay.
general type, yeah.
For general type, of course, you have some idea. The separated quiver gives one direction. So if the separated quiver is wild, then of course the algebra is wild. So you get some information, but this one is not the case. You can have a wild algebra, separated quiver as anything. And so this is difficult. And then also, even if you know the quiver and you have a presentation, then just from the quiver Q does not have enough information. So yeah, so I mean, it's rather more difficult for hereditary or something close to hereditary with we call it triangular quiver. So this is sort of easier. So you have may have quadratic forms, Tietz forms or something, but this doesn't really work so well. I think for our various classifications, the most useful thing is this paper by Ringel on Tame algebras in some old ICRA proceedings. So he classifies Tame one-relation algebras. So you have either quivers, of course, with no relation, and you know when it's finite type and when it's tame and when it's wild. So if you have a one relation algebra, then he has a long list of schemes, of frames, which he can use and say, well, if you have a frame like that, then the algebra is tame. And this is actually the most useful tool we had. But even that isn't enough, because if you have two relations, then you wouldn't know. And so it is quite difficult, yeah. Yeah. So maybe this is why not so much is known, because it's difficult, yeah. Yeah.
So any more questions? Not the case. And so thank you again for your nice talk.
Well, thank you for having patience with me about the iPad. And